Before that, in a series of lectures, we considered structures which we called metric spaces, which were some set and some function, a distance function defined on this set. So these are one of the most general objects which we will consider in this course. Well, in this course, it's the most general object. From today's lecture, we will start to consider another type of spaces, which are called normed spaces. So, in metric spaces, we try to generalize the notion of Rn, preserving the distance between any two points. Not preserving, keeping the notion of a distance between points. So now in normed spaces, we will generalize Rn, keeping the notion of a size of an element. Before we introduce a norm on a linear space, let me briefly recall what is a linear space. I believe you all know this from algebra course or elsewhere, but let me briefly recall what do we mean by a linear space. A linear space, sometimes it's also called a vector space. Is a collection of four objects. The first object is a set, space itself. The second object is a set of scalars and two operations, additions of vectors and multiplication of vectors by scalars. In this course, for the set of scalars, we will either take real numbers or complex numbers, nothing else. Then, we want that the operations, addition and multiplication, were defined on E, such that if we take two vectors from E, the sum of them also belongs to E. If we take a vector and multiply it by a scalar, then the result is also in E for every xy from E and lambda from F. Well, in other words, we want E to be closed with respect to addition and multiplication by scalars. Also, we want several properties of addition and multiplication which make this space nice. So first, it doesn't matter in which order we take the addition, or say, commutativity of addition. The second property is associative property. So the addition is nice. Well, multiplication is nice as well. And also, if we have a sum of scalars multiplied by a vector, then we have a sum of. Also, we want that if we scale vector first and then scale it again, then we get the total scaling of the vector. Also, we want that a scalar 1 exists, the scalar which does not change anything if we multiply, doesn't change the vector if we multiply the vector by this scalar. And also we want the existence of a zero element in a vector space. Let me write 0 like this for a moment to distinguish a vector 0 and a scalar 0. 0 element. Of 0 element 0 of E exists, and 0 equals to 0 scalar times any vector. Well, I believe you have seen this kind of structure before. So it's linear space or vector space. Let me briefly go with examples. Well, of course, Rn for any n is a linear space. Because, well, a linear vector space is a generalization of Rn. In the first two lectures, I have introduced plenty of examples of metric spaces. In all of them, except the one with discrete metric, the underlying set is a linear space. So let me mention a few more. So for instance, a set of continuous function on an interval, or the set LP of p-summable sequences. They are all linear spaces. Well, L infinity, the set of all bounded sequences, they are all linear spaces. And I will mention two more, which are subsets of L infinity. So the first one is C, is the set of all convergent sequences. So limit of xn exists. And one more, C0 is the set of all vanishing sequences. So it's a subset of C, subset of convergent sequences. All sequences converging to 0. They are all, these two are linear spaces as well. Okay, so C0 are subsets of L infinity, and well, C0 is a subset of C. Let us introduce a special property of subspace, of a subset. Definition. A subset F or E0 of a linear space E is said to be a subspace if it is a linear space with respect to operations of addition and multiplication by scalars from E. With respect to operations which are inherited from E. So what is said there is that if we take a subset, then it is a subspace if we take any two elements from this set, and it will belong to the same set, and if we scale a vector, then the result will be in the same space. For instance, the set C of convergent sequences is a subset of all bounded. So we take the usual addition of two sequences and multiplication by scalars. Now if we take any two elements from C, two sequences which are convergent, if we sum them up, the result is also convergent. So the result is in this set. If we take a convergent sequence and multiply it by a scalar, the result still will be a convergent sequence. So C is a subspace of L infinity. The same is true for C0. C0 is a subspace of L infinity, and moreover, C0 is a subspace of C. Now let me briefly recall the notion of linearly independent and linearly dependent system of vectors. I believe you all know that, but just to recap, lambda 1 up to lambda n from the set of scalars, not all of them are zero, such that a linear combination of these vectors equal to zero element. So if we have a bunch of vectors, if we can find a scalars, the same number of scalars, scale any of these vectors by scalars, sum them up, so to make a linear combination. If it's possible to find such scalars, not all of them are zeros, that the linear combination equals to zero element, then we call these elements linearly dependent. If it's not possible, then we call them linearly independent. A linear space E is said to be finite dimensional if there exist n vectors from E such that E equals to the span of all these vectors. Let me also recall what is a span. So the set of all possible linear combinations of these vectors for all possible scalars. If it happens that these vectors are linearly independent, then we will say that the dimension of E is n. In this case, this set x1, xn is called the basis of E. Well, as you can guess, we will define a space to be, we will say that a space is infinite dimensional if it's not finite dimensional. Definition. A linear space is said to be infinite dimensional if for every n there exists linearly independent elements x1, xn from E. you won't be surprised if I will say that Rn is finite dimensional, and moreover the dimension of Rn is n. Let us consider the linear space of all bounded sequences. What is the dimension of L infinity? Let us consider in L infinity the elements. Consider, well, the sequence of elements En from 1 to infinity, where En equals to a sequence of all zeros except the nth element. Let me go with K. That will be slightly better. Now, for every n, and any scalars lambda 1, lambda n from real numbers, we consider this space over the field of real numbers. It can be equally done, it can be equally considered over the field of complex numbers, but let's stick to the real numbers. Now, if we take lambda 1 and 1 plus and so on up to lambda n En, then what we will get is the first n elements of the sequence will be lambdas and then all zeros. So this sequence equal to 0, well, vector 0, if and only if all the scalars are 0, which means that for any n, the collection of these vectors is linearly independent. So for every n, we can find n vectors in L infinity such that they are linearly independent, which means that the dimension of L infinity is infinity. An exercise. Determine the dimension of the set of all continuous functions on the interval AB. And let us speak about the notion of a factor space. So let us take a linear space E and a subspace. Now let us use this subspace to define a relation on the whole linear space. We will say that elements x and y from E are related in this case we write x relation y if their difference belongs to a subspace. You can remember that we have considered a similar thing when we constructed a completion on a metric space. So in that case we called two sequences related if they have the same limit. Or in this notation, we call them equivalent if their difference, x minus y, belongs to C0. The sequences converge into 0. Well, it's not difficult to see that this relation is an equivalence relation. Indeed, x is related to x, so it's reflexive, because x minus x is 0, and 0 belongs to E0 because it's a subspace. If x related to y, then y related to x. That's the most evident. And if X related to Y, Y related to Z, then X related to Z. Again, fairly easy to see it from the definition. Which means that the relation we introduced is an equivalence relation. As we discussed before, for an equivalence relation, we can define equivalence classes. If we take an element from E, then its equivalence class consists of all elements from E such that Y is equivalent to X. For any X from E. As we discussed previously, two equivalence classes are either coincide or disjoint, do not intersect. By considering equivalence classes then, we construct a partition of the linear space. And using these equivalence classes, we will introduce factor space E factor E0 to be the set of all equivalence classes generated by all elements in E. So we consider a new set of equivalence classes. E itself is a linear space. So can we make this set to be a linear space? To be a linear space. To make it a linear space, we need to define an operations of addition of two equivalence classes and multiplication of equivalence class by a scalar. If we take one equivalence class and add it to another equivalence class, we set it to be an equivalence class generated by a sum. And if we take a scalar, then the scaling of an equivalence class, we set it to be, by definition, an equivalence class generated by a scaled vector. I leave it for you as an exercise to check that this addition and multiplication by scalars are well defined on this set. So with these two operations, this factor set become a linear space. And this set with these linear operations is called a factor space. Let's go a little bit deeper in all these constructions. So when I'm saying that it is a linear space, by definition, a linear space has zero. There is a zero element exists in any linear space. So what is the zero element of this linear space? By definition of zero, we have that 0 equals to scalar 0 times any element. The elements in this space are equivalence classes. By definition of multiplication by scalar, we get that this is equivalence class generated by 0 times x. Which is, since E is a vector space, which is an equivalence class generated by 0. Let me avoid the confusion to write that this one is 0 of a factor space and this one is 0 of E. These are two different 0 elements. So now let's figure out what is the equivalence class generated by 0. By definition of equivalence classes, an equivalence class generated by an element is a set of all elements from E such that these elements are equivalent to 0. Now, let's recall how we define the equivalence relation. we said that x equivalent to y if their difference belongs to E0, which is the set of all x's from E such that x minus 0 belongs to E0. But x minus 0 is x. So what we got here is equivalence class generated by 0 is all x's from E such that x belongs to E, which is, all x's from E such that x belongs to E0, which is E0. When we consider factor spaces, we assume that E0 is a subspace, which means that, by definition, it is a linear space in its own right. So E0 is a linear space, and we can speak about the dimension of this linear space. Let us also speak about the codimension definition. Let E0 be a subspace of a linear space E. We define a codimension of E0, codimension of E0 is a dimension of a factor space. That is, codimension of E0 is dimension of a factor space. Let's consider an example and compute a codimension of C0 in C. So first of all, before even we go to the codimension, what is the dimension of C0? So when we computed the dimension of L infinity, we considered sequences which are 0 everywhere except one component. And we proved that any finite number of that sequences is linearly independent. So that was our construction. But in fact, all that sequences, En, which we consider, they are eventually 0. There is only one non-zero component. So all that sequences converge to 0. So in fact, they sit inside C0. So C0, by the same argument, is infinitely dimensional. For an equivalence class in the factor space, we have. So X consists of all sequences from C, all convergent sequences, such that X minus Y is in C0. So X minus Y then converge to 0. They are both convergent to some other limits. And Y belongs to an equivalence class of X is X if X and Y converges to the same number. Which means that this equivalence class is determined by a single number, say A, which is the limit of Xn. Indeed, this class consists of all sequences which are convergent to A, as we just stated it over there. So the equivalence classes in this factor space are determined by a single number. This tells us that this factor space is nothing but a real line in disguise? Well, to be more precise, it is possible to construct a bijection between the factor space and the space of real numbers, and the bijection will be from a real number A to a set of all sequences converging to A. Well, this means that the codimension of C0 is the dimension of C over C0, which is 1. Let us now finally get to the notion of the normed linear spaces, which I announced at the beginning of the lecture. So now we will take a linear space and equip it with some extra tool, which we call a norm, and which will help us to measure the size of elements in a linear space. Definition. Let E be a linear space. Now, let us consider a function which takes an element E and returns a number, a real number, from, so it's a function from E to real numbers, and we will call this function a norm if it satisfies several properties. First, we want that this function to be so sometimes we will subscript the linear space over here to show that it's a norm of this particular space. If it will not lead to any confusion, we will not. So in this definition in particular, we have only one norm, so I will not subscribe E over here for simplicity. So we want this function to be non-negative. Well, this norm is a kind of an analog of a size of an element. We want that the size of our vectors to be non-negative. And we want it to be equal to 0 if and only if x equals to the 0 element of a vector. Also, we want that if we take a scalar multiple of our vector, then we can factor out an absolute value. For every vector and for every scalar. And as a third property, we want the triangle inequality. And if we have a linear space and we have a norm defined on it, then we will call a pair of a space and this function a normed linear space. Before that, we have studied metric spaces. Now, we have a new object in our hand, normed linear spaces. Are they related somehow? Well, the answer is yes. So every normed linear space is a metric space. Well, how to define a metric if we have a norm? So pretty much like we did it in Rn. So there, a length of a vector gave us a size of the vector, but if we want to find a distance between two vectors, we subtract them and then measure the length of them. This is exactly what we will do here. So we will define a metric as a norm of a difference. It's not difficult to see that having these three properties of the norm, this function is a metric in fact. But it is slightly more than just an arbitrary metric. A couple of very nice properties. So the first property is that rho of x plus z and y plus z equals to row of x and y, which means that this metric is shift invariant. So if we take 2 points shifted by the same vector, the result will, the distance between two of them will stay the same, which is not true for a generic metric. And one more property. So every metric of this form additionally satisfies properties A and B. It turns out that the converse is true. If we have a metric which satisfies A and B, then it is in fact generated by some norm. Having metric in hand, we can speak about the convergence. So we have the notion of distance. We can speak about convergence, and in particular, we can speak about completeness. The complete normed spaces are so nice that that they have their special name. They are called Banach spaces. That was a Polish mathematician, Stefan Banach. So he has done a lot of stuff in functional analysis, and even in this course, till the end of this course, we will see his name several more times for various different results. Let us now speak about some examples. Rn, I will write P over here. Before that, I did that for the metric. Now I will write down the P norm, and you will see a lot of similarities. Well, again, you won't be surprised that we consider the space Cn with exactly the same norms. Let's write a few more examples. Complex continuous functions on the interval AB with the uniform norm. All these normed spaces are complete, so they are all Banach. Let me write down the fourth example. That will be a space of all continuously differentiable functions. If we equip this set with the infinity norm, let me write it like this because there is no F here. So if we take this uniform norm for this set, then this set is incomplete. But in fact, by the definition of completeness in terms of Cauchy sequences, completeness is defined by the metric. So in our case, by the norm. So is it possible to find another norm such that this space will be complete space? Yes, it is. So if we consider the same space of once continuously differentiable functions, and now we will take the norm of an element to be the infinity norm of the function itself plus the infinity norm of the derivative. And then with this norm, this space is Banach. Okay, after having considered a couple of examples, let us go back to our factor space. So we already know that it is a linear space. But now we have a new notion of a norm. So is it possible to introduce a norm on a factor space? Let us take a linear space and its subspace. Now, for every x from our linear space, we consider the corresponding equivalence class consider the corresponding equivalence class, which is an element of a vector space, and we will define the norm of this element as an infimum of norms of x minus y when we take infimum over all elements from E0. Yep, this is the norm in E. So here in this statement we have two different norms. So this is the norm in E and this one is a norm in a vector space. So that's why I will use this subscript. So the claim of the theorem is that the norm, the expression defined in this way is a norm on a vector space. So let us check the properties of the norm. Well, first of all, this is in fact a function from the vector space into real numbers, because this norm, the value of this norm are real valued and theorem of real numbers is a real number. So let us now check the axioms. For the first axiom, it is straightforward that this norm is greater than or equal to 0. Because by definition of the norm, this norm is greater than or equal. I'm saying norm already where we just proving that this is a norm. That expression, so this expression is greater than or equal to 0. Because by definition of this norm is greater than or equal to 0. Taking the infimum, it will be also a non-negative number. Let's prove that this expression is 0 if and only if the equivalence class is 0 in the vector space. So first of all, the easy part is if the equivalence class is 0, remember that the 0 in a vector space is E0 itself. Then the norm of this is infimum where this little x is a representative of this equivalence class. So x is also from E0 and y is from E0. So, but E0 is a subspace, so in particular it contains 0. So taking the infimum over the norm of elements which are in E0, we get 0. Well, since in this case the difference is in E0. Conversely, let us suppose that this expression is 0 and show then that the equivalence class is 0. This means that infimum is 0. By the definition of infimum, there exists a sequence yn yn from E0 such that x minus yn converges to 0. Okay, that's the place where I realized that I forgot one very important assumption over here. This subspace should be closed. If it's not closed, that it will not work, because now I'm about to use the closedness. Well, this fact means that, well, just rewriting, or it means that yn converges to x. And now, since E0 is closed, then x belongs to E0. Well, we are done with the first axiom of the norm. The second axiom is straightforward. Let's now prove the triangle inequality. So first of all, we have that the norm of the sum of two equivalence classes is, by definition of that expression, is an infimum taken over all z in E0. Also, let me write down the definition of the norm of equivalence class of x and equivalence class of y. Well, I will limit myself to writing this once. For y, it will be exactly the same statement, just replace x by y. By this definition, there exists absolute greater than 0 and V1 from E0 such that x minus V1 norm in E less than or equal to the right hand side plus epsilon over 2. And the same for y. Now let me take this expression and write it as infimum of x plus y minus v1 minus v2 minus v and minus w for all vw in E0. That's exactly the same statement. Now I will split it into two infimums. So this infimum is taken over the whole subspace E0. So if I just replace this infimum over the whole space by v1, then I will make this expression not less than it was before. And the same story here. And now I will use these to estimate. Since epsilon is arbitrary, we conclude the triangle inequality. And we're done with this proof. One more comment, it's in fact a very important result, but I don't even have time to write it down, not even to prove. So we already know that if we take a non-linear space, then the factor space is a non-linear space as well. Moreover, if the original space is Banach, then the factor space is Banach as well.